This is the 6th lecture, and my goal here will be to put Maxwell's equations in the form of differential forms, and you will see the great advantage that comes out of that. But first, let me remind you a little bit about Maxwell's equations in the form that we teach them today. So we have these written very concisely. Divergence of E is equal to rho. And if you're worried about 4 pi rho or rho over epsilon, forget all that. They can all be absorbed into the definitions of rho or J, as we'll see. That is the equation for the divergence of E. We also need an equation for the curl of E, which is minus dB by dt. And then we have the same thing for B. This is the equation that tells you that there is no magnetic monopole, that there's no source which is that of a charge. And then the curl of B is J plus dE by dt. This is the famous Maxwell displacement current, the one that he guessed, which then led to the wave equation, which then led to the discovery of electromagnetic waves, and so forth. Okay, so then if the let's now solve this as best as we can in the most general form, and knowing that these are differential equations which can only be solved if you have particular boundary conditions. But this immediately cries out for a solution. It says that B has to be equal to curl of something, let's call that A. Curl of anything when put over here is 0 because divergence of curl is 0. Okay, so that solves this equation. Then we have, let's put this in here. So then we have curl of A equals J plus dE. But before that, let's before inserting this in here, let's look at these two over here. If I take B equals to curl A, or so I have curl of A equals J plus dE by dt. Now if we look over here, now if we put B equals curl of A over there, then I have curl of E is equal to curl of minus curl of dA by dt, which means that I have the curl of E plus dA by dt equal to 0. And if the curl of something is 0, then that means that this thing is the gradient of something. And so we can call it phi. Which means that, okay, E plus dA by dt is equal to the gradient of something. That something is the potential, and we could put phi equally well, we could put minus phi. And so from here, we have E is equal to minus gradient phi minus dA by dt. And this is a vector, of course, all of these are vectors. So I have B in terms of A and E in terms of A and phi. A is what is called the vector potential, and this is now what we can do is we can put like over here in these two equations. So we can put E equal to that, and we'll get a second order differential equation here. Then we can put B equal to curl A, like I did over here, and then use an identity which will give us minus del squared A plus gradient of divergence A equals this. And that's the way that you solve it. That's the way that you write Maxwell's equations when you want to solve them in one particular frame. But then there is a much nicer way, and that is when you ask what happens when you put Maxwell's equations in a frame that is moving relative to you. And so that's when you need to make a transformation of coordinates. Then the relativistic form of Maxwell's equations emerges, and you define what is called the electromagnetic tensor F mu nu, which is defined as d mu a nu minus a nu minus d nu a mu. This is an antisymmetric tensor quantity. You reverse mu and nu, you see this changes sign, and then these equations take a very simple form. Now what I will do is I'll go very quickly to the relativistic form, which I assume you know, but it all starts from here. And so I just want to show you a few slides before we get back into differential forms. You will see that compared to the form of Maxwell's equations when they're written down in a particular frame, the general form is so much nicer. So I have these are from a talk I gave some time ago. This paper, which laid the foundations of electromagnetic theory, was written in 1865, which is about, well, 200 years ago, well, almost 150, okay? This is how Maxwell actually wrote them down, and you can see how ugly it is. It is 20 equations. I wrote down 4 before you. Just see what's over here. You need to absorb this. And they're entirely the same as the ones that I had written down, except that the notation is very ugly. And just a few years later, there is an electrician who was only educated up to high school. He invented the notation which you just saw, and at the University of Edinburgh, under Maxwell's statue, this is what is carved. Now you have mugs, t-shirts, and Maxwell, of course, is the big god in Edinburgh. Steven Weinberg, who said, okay, things will change, but for the next 1,000 years, maybe even the next after that, you may worry about the t-shirts going out of style, but you won't have to worry about electrodynamics becoming false. And yeah, this is one of his famous quotes. Okay, so how do we teach Maxwell's equations? In relativistic form. As I said, you define what is called the field tensor, and then you can also define what is called the dual field tensor. That is, you multiply by the Levi-Civita tensor that gives you F tilde. And then look at the beauty of this, that you had 20 Maxwell equations which are now boiled down only to 2 equations that look like this. And it should be good enough. I mean, in terms of beauty, this is already very beautiful. But maybe it is not so beautiful because it's got all these indices. You are confining yourself to a particular set of coordinates, and you want to get rid of coordinates. And differential geometry and differential forms and all of differential geometry is trying to understand what it is that is geometrical and what it is that is dynamic. So we would like to get rid of these indices today, for which we will need to develop new concepts. And when we do that, we will find that Maxwell's equations, all those 20 equations, will be reduced down to just this. Now, I don't know if I will succeed in 1 hour, but that is going to be the goal. And I should say that in the 2 lectures that we have remaining, I will try to get Einstein's equations also in a form that you can put on a matchbox. So that's the goal, and let's hope for the best. By the way, those were Maxwell's equations written down in flat space. But it is then trivial to go to curved spaces. So suppose that you're doing electrodynamics near a black hole. Then all you need to do is interpret F suitably and what will be called the Hodge dual of F suitably. And there'll be a metric tensor and a determinant, and that's all that you will need. So recall that dx mu is a form, one form, which acts upon a basis vector and gives you delta mu nu. Any vector v can be written as v mu, and so I should emphasize any, and any one form is, let's call that general one form A. Okay, and all these live on TP of, so the vectors live on TPM and the forms live on TP star M, the dual to this. At this point, we have only one forms, and now we will define what is called the wedge product of two one forms. So you see, when we talked about vectors, we talked about multiplying vectors, and we said there's something called the dot product. The dot product of A dot B we defined as G mu nu, A mu, A B nu. Now we need to define a product of two one forms. And okay, so if I take dx mu wedge, this wedge operation is the multiplication of two one forms, and multiplication is only then meaningful when I say what it is. Well, the most important thing is that this is antisymmetric, and that immediately says that this is if I have two indices which are equal, then this is equal to 0. Because if something is equal to minus itself, it's got to be 0. Fine. This is associative, meaning that if I take so this is linear and associative. That means that if I multiply this by some number, then this thing gets multiplied by the same number and so forth. So the usual properties hold over here. Now, this is very much like the cross product, and in 3D, we would have dx, dy, dz as three one forms. And dx, dy. This is the same as the cross product there. The cross product tells you what? It's the area spanned by, it is the area of, so if this is dx, dy, then dx cross dy is the area of this parallelogram. So it's the area of this, and it has a direction. You know that area is not a scalar, it's a direction. It can point this way, one way, or the other way, that is perpendicular, in the perpendicular direction, in the z direction in this case. The importance of this is that when we change coordinates, so I'll do this in 2 dimensions, and then you can see immediately that this generalizes to any number of dimensions. Let's say that I have x prime is equal to some function of and y prime is a function of x and y as well. So if you were to do simple calculus, this one over here will tell you that when I make a small change in x and a small change in y, then the small change in dx prime will be and similarly dy prime will be now so this is from ordinary calculus. Now we want to regard this as a transformation of forms. So let's say that dx and dy are forms, and then we make a transformation. Then dx prime and dy prime are the transformed one forms. So let's see what this wedge product transforms as. By the way, I need not repeat that this is a machine. This is a one form, this is a one form, and in order to get a number out of it, I will have to make it act upon vectors ex, ey. It eats vectors, and in that way, this over here will become a number and an area. So all that is implicit, it's understood. Any questions so far? No? Straightforward, huh? Okay, can anyone guess what will happen when I take dx prime wedge? Well, let's not guess, let's do it. So there I have and then I have one form here, one form here, here, and these are to be considered constant coefficients. Why constant? Because we are at one point. We are at the tangent plane itself. Now dx, wedge dx is 0. dx, wedge dy is dx dy, dx wedge dy. This into this is almost the same, except that x and y have been flipped around. So this will give you minus dx wedge dy, and this into this will give you 0. So this is equal to Now that is nice. Did I do something wrong? Yes. Yeah. This into that dy. Yeah. And then dx prime by dy, dy prime by dy. X. Yeah. Right. Now this is our original volume, original area, and this you can write as so dx. Let's and what did I do over here? D. So I have to have this into that. And then this will be if I have 3 variables, then this will be x prime, the next one will be x prime, then this will be x, y, z, 3-dimensional matrix, 4-dimensional matrix, and this is the determinant of the Jacobian. So this is actually interesting because it's telling you that when you make a change of variables in solving an integral, you have to deal with the Jacobian and with an oriented area. And in 3 dimensions it's okay, we can visualize it, but what when we go to multiple dimensions? Then something like this dx, dy, dz, dw, what does that mean? Well, it will mean a volume in so many dimensions. Right. After this, I want to define the D operator. I'm forgetting what it is called. What is it called? Exterior derivative. Yes, thank you. And we have to define it. We have to invent it. So let's take some guidance from ordinary calculus. If I have just one, suppose I have a function only of x. There is no y, z, anything, only x. Then if I ask how much is the change in f when I change x by a little bit, then this is df by dx. And so I will say f is a zero form, and df, because it's got dx over here, is a one form. Now, if I have a function of n variables, then calculus tells you how to do this. If I make a small change in any of these variables, then df will be df by dx mu. And so D has converted a zero form to a one form for any number of dimensions. So that's one thing that we require of D, that it be a form raising operator. Now, this so in general, if alpha is a P form, then D alpha will be a P plus 1 form. Okay, next we say that we define the action on on a product, on a wedge product. So these are both forms. One can be, so when you stack up forms, this will have some number of dimensions, and this will have some number of dimensions. Then we would like to define its action on this. And we'd like to do this in a way which is consistent with the rules that we know. We know that if I have d of f into g, then it will be df into g plus f into dg. And so we would like this to be d alpha wedge beta plus alpha wedge d beta, except that this is not quite right. We have what we want is the d operator to go through. If beta is a second has rank 2, then it's okay. But if it has rank 3, we have then missed one minus sign, and so this will be plus minus 1 to however many we have missed over here, P. And finally, so this is part of the definitions that remember that we are requiring D to have these properties. That D squared is equal to 0. If D acts upon itself, then that will give you 0. Now you can ask yourself, why have we required these properties? After all, we are the creators of the exterior derivative. So why as creators have we given such properties to our creation? And again, the answer is from the rules of ordinary calculus. This says nothing different from ordinary calculus, but is just a very concise way of expressing things. Okay, now let's start creating one forms. Let's start creating forms which are not trivial. So let us start with a one form. The most general one form, and explore what happens when we apply D to it. So given our goals, what is the one form I should start with? What's the most general one form? What? Give me an example of a one form first of all. Okay. What? Say it again. No. What is the most primitive one form that is in your mind? Most primitive. dx, dy, dz in 3 dimensions. What about 4 dimensions? dt. So in 4 dimensions you will have dt, dx, dy, dz. Nothing very big about that. So what's the most general form of a one form in 4 dimensions? Most general. Just a linear combination of them. Yeah? Something times dt, something times dx, something times dy, something times dz. And what's the nicest way of writing that? I'm not saying this is anything to do with electromagnetism. I don't know what it is. These are the most general things I could write down. Okay, now let's apply the rules of D to this. So this implies that D A. Well, the rules of calculus say that D should be applied here, and then D should be applied to And what does this say? Which means this is 0. Very good. What is the rules? What is d of a nu? What is a nu? A nu is a function of x. When I said that a is equal to a nu of this a nu, yeah, it's a number which is at a particular point on the manifold P. That point P has got coordinates x. So this is a nu of x, where x is on the manifold. Now, what's the d of this? Isn't it exactly what was over here? So this is equal to d a nu by d x mu dx mu, and now I have this thing over here and dx nu, but this makes no sense because I am dealing with one forms and we have a product and must have a wedge product there. So this is okay. Any questions, any confusion? Everything clear? So I'm getting no challenges. Okay. Yeah.
So did we define the A in same dimensions as the X number of dimensions?
Okay, so yes, absolutely. If we are in a two-dimensional space, there will be two coefficients. There will be two basis vectors and two coefficients of those basis vectors, which are different at different points on the manifold. Hence, we call them functions of P or x1, x2, x3, etc. Okay?
Okay.
What?
But that is in the dual space, right? And the spatial dimensions we are dealing with are in the real space.
Yeah. Okay. So we talk of a manifold. A point on the manifold is determined by n coordinates, which means that there are n different directions which can be chosen orthogonally. These then make the basis vectors, and to each basis vector there is a basis form in the dual space.
Right.
So everything is very nice, very consistent.
Thank you.
Okay. Right, so now let's look at this. So we have dA is equal to see, this is anti-symmetric. This doesn't have any particular degree of symmetry. I'd like to write it more nicely. This is nice, this is okay, but I can write it even more nicely. So let me call nu mu and mu nu. Just these are dummy indices. So I have plus but what must I do? I should then divide this by 2. This is exactly the same as this with mu and nu indices exchange. But you know, looking at this, I can now bring this here. I can flip these two over. And so this is half and I don't like writing this all the time below, so this is d mu. Done. What is this thing which you have seen all your life? Electromagnetic field tensor. This thing is what you call F mu nu. So the whole thing good. So this is such an important result that I now need to rewrite this over here. So I'll write my two things here. This will and now I can wipe out that way. But now I have made huge progress. Huge progress. Because if I take d of dA, because d squared is 0. So this says that d of and what is this telling me? This says I have to have d of F mu nu wedge, because this, remember, d, this is a number, matrix of numbers, but number. So this is a one form, wedge dx mu, wedge dx nu. And now this is df mu nu by dx rho dx rho and I always like my indices mu, nu, rho. Is no harm if I keep it this way, But just like I like to write 1, 2, 3 as 1, 2, 3, not 1, 3, 2, what I will do is I'll take this across over here, I get a minus sign, because when I exchange two 1 forms, I get a minus sign. Then I take it across again. And on the other hand, if I had 3 over here, 1, 2, another 1, then I'd have to make 3 leaps, which means I'd get 1 minus sign at the end. And that's why the differentiation had that minus 1 to the p. Okay, so this is and so I have a 3 form now. We started off with a 1 form, got a 2 form, and then took the exterior derivative of that and got a 3 form. And now we have this 3 form relation over here. So now let's explore what this is about. In 4D, we are in 4D because mu rho r, they take value 0, 1, 2, 3. And this is the Einstein summation convention with all of these. You know? Let's see what this is telling us. So we can write this all out. And so it will be a lot of terms, and we have to now do this. Should we start with taking rho to be 0? Then we let rho equal to 1, 2, 3. That's all that rho can take. Or let me write it this way. First let rho be equal to 0. And then we'll take it to be 1, 2, 3. Okay, so if rho is 0, this is d by dt. So then instead of writing d by dt, let me write it just d0. d0, tell me what mu and nu can be now. You see, if rho is 0, then mu or nu cannot be 0. So this can be 1, 2, 3, This can be 1, 2, 3. And of course, they cannot be equal simultaneously. So ij dxi dx0 is the same as dt. Okay, but I cannot stop here. Now I have to let rho be k. Let it be k. If rho is k over here, then what can mu and nu be? They cannot be k, but they can be 0 as well. So let's explore all possibilities. So and this will be that's possible. By the way, what is this ijk 3 form? And suppose this was 1, 2, 3, what would it be? Be a volume element like dx, dy, dz. Because all this, when it acts on a basis vector, it will give you scalar. Yeah. Okay, then what else are we missing out? So yeah. I'm sorry, I didn't get you. I said let. In over here, yes. So we use the notation that mu, nu, rho are 0, 1, 2, 3. I, j, k are 1, 2, 3. That's a good way of avoiding confusion. Okay. So now what else? In here? No, I cannot be 0. But you're right. I have not included all terms as yet. So what is missing over here? See, we have fixed. We have said that first row was 0. Next it is k, which is 1, 2, 3. In which case this will be 1, 2, 3 combination. What is missing now? Yeah. So then I have dk f0i and What else? Okay. Yeah. So, but that will be the same as, okay. So this can be 0. This is here 0 and this is I. Then I can have this as I and this 0. But then this and this will be exchanged with each other. So that is the same thing. Okay. So then this says, let's get this in the same, okay, so let's look over here, D0 Fij, and I can take this over here. So let's do this. Is that right? This plus this is that. Now, एक मिनट ना इसमें गड़बड़ है, इसमें जे के ये जे है, जे आ गया, हाँ हाँ, we're almost there. What is this thing over here? dk Fij, and Fij you could write as this multiplied by this. This now, can you see that this is why? Remember what Fij is. Exactly, this is Bk. So, straight out this says divergence of B is equal to 0. Because it is multiplied by something anti-symmetric, so therefore this is exactly that. So this Fij is taking the anti-symmetry is just B, and then this is dk into Bk. B dk equals divergence B equals 0. Yes.
In other way, can we say that when we apply the derivative on Fij, it has the same number of dimensions, and since we have a wedge product on the other side, and we know that the wedge product of two similar terms is 0, eventually we will get 0.
0 for what?
0 for the second, for the term we wrote delta dot B. If we simplify that mathematically.
Well, I have done things mathematically, so can you tell me a little more?
Sir, I'm saying if we apply the derivative on Fij.
If I apply the derivative dk on Fij,
Right.
that's not 0. So this is Fij is di aj minus dj ai, right? When I apply dk, then I'll get dk di over here and dk dj over here. But I and j are not equal to each other. So in fact, you know, this over here performs the task of and so therefore this becomes bk, it becomes divergence of b equals 0.
So, but we have like derivative of x and xi, xj and xk, right? All I'm saying is like they are 1, 2, 3 in specific. So when we apply the derivative and we put the indices, we will have some terms similar.
Let me okay. So you want me to write F12 as, what do you want me to do next?
Apply the dk.
Which k? 3 or what else?
So
Okay.
it will expand, right? And
So this will be so what? I don't get this equal to 0. It's only when I do the sum that I will get 0. See, the divergence of b equals 0 doesn't mean that d1 b1 is equal to 0. It means that d1 b1 plus d2 b2 plus d3 b3 is 0. Okay, so hopefully that is behind us.
but I'm not satisfied.
Okay.
Like, I mean, how will we prove it mathematically? We just put b, like, you know, we just related things, but we haven't derived it completely.
Okay, so then I was trying to do this. Let me.
I guess it's not that del dot f is this whole term along with this wedge product is 0. So,
Okay,
yeah.
so
one is symmetric, other is anti-symmetric. You can think in this way.
right. Let me put. So what is this wedge product over here? It's a 3 form. 3 form eats vectors for lunch. Give me a lunch. PQR. PQR is not good. PQR, okay. So I will give it EP, EQ, ER. All right. And so this then will give me epsilon PQR. That's a number. Okay. Now that means that I have epsilon PQR dP FQR. Now I hope you will be satisfied. Take, first of all the indices are rightfully contracted. Now what this is
6 terms. And
Just write them out.
so remember that Fij
Is minus Fji.
so then this will reduce to,
Exactly this.
okay. Since we have very little time, let me say that this is exactly the same. Now, this is also equal to 0, and this is saying that when I this is giving us our other Maxwell equation, which was what? Divergence of what was the other sourceless equation, Maxwell equation? So curl of no. See, it was one of these was divergence of B equals 0, and the other was curl of E plus and now let's see if we can recognize this. So we have a d by dt which is over here, and we have F0i is E, yeah, and so we have exactly that over here also. I have worked it out completely in the notes, so you can go and look at it. The best thing is to derive it yourself. But then these are 50% of the Maxwell equations. I have to do another 50%, and I have only 20 minutes left because we started 5 minutes late. For that, there is another concept which is needed, which is called the Hodge-Star operation. Suppose we are in 3D. 4D is direct extension. Then if I take a 1 form and if I take a 0 form, the Hodge-Star operation will take the 1 form into a 3 form. Star of 1 is a 0 form. Any function over here. Okay, let's make it an f. F is a 0 form. Then by definition, this is f what's the next form? 1 form. So give me an example of a basis 1 form. Dx, very good. Now it's becoming simpler. So suppose I have 2 form. What do you think this will give me? Dz. and this will give me 1 scalar. So suppose, yeah, f is 1. So whatever dimensions of the space, if it is n, then you can have n basis vectors, correspondingly n forms at most. They are complementary. They are duals, exactly. And I can't go higher than this. There are no more forms over here. What will happen in 4 dimensions? Well, I have dt as well. So in general, you will write dx mu, dx nu, etc. Okay, so then with any form that you have, you will have a dual. You will have a Hodge-star dual, and then it's a matter of working out that dual. What did we have for f? F was is so can I take its dual? It will not be the same 2 form, but it will be another 2 form. And now, if I take d of this, what will this give me? A 3 form. Yeah. By definition, what a d form, what a exterior derivative does, it raises your form level by 1. Good. Now let's come to, so keep in mind that what we want to do is and that means that we also need to understand what will happen on the right hand side. So J, this is the same J that occurs in Maxwell's equations and whose 0th component is what? Is the charge density, and whose vector components are Jx, Jy, Jz. Okay, so J written as a vector will be rho dt. I'm writing it wrong for now, but it's okay. The only thing is that because our metric has got a negative sign, this will be a minus over here. Okay, so what will happen if I take the Hodge dual of J? What will it give me? It will give me a 3 form, right? Since we won't have time to complete the calculation, all I will say is that work out this form. Well, we've already worked this out, but I'll write down the answer from there so that you see exactly what it is. Then you work out its dual, you take its exterior derivative, 3 form. Here is what we know from our definitions in electrodynamics, that this is a vector. This is a 4 vector with components rho, jx, jy, az, and then this is a 3 form. And now just to, since we don't have time to go through all that calculation, maybe I will just see if I can find, my computer has gone to sleep. Wake on. Yeah, I have located it, hopefully somewhere. So if you write it out explicitly, plus, and then there'll be the B components. So this is exactly that. When you open it out, see there dx mu, dx nu, so it's exactly that. And dual of F and then there'll be the electric part, which is See, it's all cyclic, so it's not so hard. Okay, so that's D of that. And now the two Maxwell's equations that you have, which are, okay, so now take dual of this and equate it to the dual of this. So you have three forms on that side, three forms on that side. Match the coefficients, and the two other Maxwell equations, the non-homogeneous ones, they also fall out from this. So what's the advantage of all this? Okay, we got rid of the indices, but so what? You see, the homogeneous ones, we didn't even need to ask what is this A, what is A mu? It's like automatic. So that's a part of the geometry of the manifold. There's no dynamics over there. The dynamics comes from the forcing term, which is J. And so F is then forced by J. And here is the whole beauty, that you can reduce most of it to just the geometry. The dynamics comes in when you say that there is something external to the system. J is external to the system. What is it? You have passed current through a battery. Now, you did something externally, or you threw a laser beam at an atom. That's an external intervention. Furthermore, you can do this in a curved geometry. So if you want to do the bending of light, this is the equation that you should use. If you want to ask about how light will behave close to a black hole, or as it passes through a black hole, you will use this electrodynamics. The only thing that I have omitted was this thing, square root of G. You remember that G is G mu, so G is related to the determinant of G mu nu. If G mu nu is flat, it's ones or a minus one, then this thing is just equal to 1. Otherwise, this is perfectly general. So that is the beauty of that. And next time then we will talk about general relativity. Good. Any questions now, or we can, yes. Mike, please. Mike.
सर हमने F को कहा ना कि वो उसकी 2 फॉर्म है, और फिर हमने डुअल F को भी कहा कि वो उसकी भी 2 फॉर्म है. इट इज़ बिकॉज F म्यू न्यू की वजह से हमने ये बात की है. अदरवाइज तो जब हम हॉट स्टार की बात करते हैं तो हम कहते हैं कि,
हम किसकी बात करते हैं?
हॉट स्टार की बात करते हैं तो हम कहते हैं सर आवाज़ आ रही है?
हाँ.
सर मैं ये कह रही हूँ कि F जो है वो हमारे पास 2 फॉर्म है ना उसकी. फिर हमने जो हॉट स्टार F की बात की उसकी भी 2 फॉर्म है.
बिल्कुल.
तो पहले हमने ये बात की थी कि हॉट स्टार जो होता है वो उसकी फॉर्म को रिड्यूस करता है. लाइक 3 है तो वो 2 में लेके जाएगा, एंड देन 1 में, और फिर 0 में, स्केलर में, जो हमने वहाँ पे उसकी 3-4 स्टेप्स लिखे थे.
हॉज 0 फॉर्म को 4 फॉर्म में ले जाता.
नहीं 4 को 1 0 फॉर्म में लेके आया था ना सर. सर वो जो हमारे पास एक्सटीरियर डेरिवेटिव
देखे
था
ना?
ना,
हाँ।
वो हमारे पास इंक्रीज करता है फॉर्म्स को।
तो ये अगर इसका मैं हॉज स्टार लूं तो ये तो ये देगा ना, और 4 times in 4 dimensional space.
डायमेंशन में ये भी देगा 1 to dx which dy which dz ये नहीं होगा 4 डायमेंशन। 4 डायमेंशन में अगर हम zero
सर वो बेसिकली फॉर्म को रिड्यूस नहीं करता हमारे पास, मैं ये पूछना चाह रही हूँ। मतलब पहले तो हमने ये देखा था कि वो उसको रिड्यूस कर रहा था फॉर्म्स को। लाइक अगर 4 फॉर्म्स थी तो फिर हम वहां से चलते चलते 1 तक पहुंचे थे।
हाँ,
तो यहाँ पे अगर ऐसा नहीं हो रहा कि वो दोनों 2 फॉर्म्स ही रह रही हैं, तो मैं ये कह रही हूँ कि इसकी वजह एफ म्यू न्यू है, वो जो हमारे पास वहाँ
एफ
पे
न्यू तो कंपोनेंट्स हैं ना।
तो सर
एफ
इन दोनों
एफ तो 2 फॉर्म है ना।
यस सर।
ये 2 फॉर्म है। अब मैं इसका जब हॉज ड्यूल लूंगा तो वो भी 2 फॉर्म बनेगा।
क्यों?
क्यों? इसलिए कि 4 dimensional स्पेस है और वो 2 से बढ़ाता है या 2 से कम करता।
तो सर लेकिन जब पहले हमने इसकी बात की थी तो यहाँ पर तो वो इंक्रीज डिक्रीज कर रहा था ना।
नहीं, ये आपको उसका ड्यूल देता है ना, हॉज ड्यूल देता। तो चलिए अगर हम 3 dimensional स्पेस लें तो अगर मैं ये लूं तो क्या बनेगा?
dx और dy।
ये ना। अच्छा, अगर मैं ये लूं तो फिर क्या देगा?
dz।
और अगर ये लूं तो फिर
1 देगा सर।
फिर वन देगा, नंबर 0 फॉर्म देगा।
सर अब इन दोनों को कंपेयर करके आप मुझे बताएं कि वो किस तरह से दोनों
अच्छा, अब मैं 4 dimension और 3 dimensions को नहीं कंपेयर करूंगा, मैं 4 को 4 ही के साथ करूंगा। ओके,
यस सर।
अच्छा, तो मेरे जो बेसिस फॉर्म्स हैं इनको मैं ये कहता हूं, 4 हो गए, कोई से भी 2 ले लो। इसका मैं हॉज लूंगा तो क्या मिलेगा मुझे?
dy dz।
यानी कि 2 का फर्क आ गया। मैं यही तो कह रहा था ना कि 4 dimensions में जब मैं 2 फॉर्म का हॉज ड्यूल लूंगा तो 2 फॉर्म मिलेगा।
ओके सर, मैं फॉर्म्स को डायमेंशंस के साथ कंफ्यूज कर रही थी।
ठीक ठीक। और ये देखो कि जब मैं जे का हॉज ड्यूल लूंगा तो वो 3 फॉर्म मिलेगा।
यस सर, बिकॉज वो 4 डायमेंशन।
Yeah. And so this gives you the possibility of doing electrodynamics in any number of dimensions. And I am not an expert at this, but I think it is not possible to do it in all dimensions. Only in some dimensions can you do it consistently.